Oh, okay, I'm sorry. We're looking for the derivative of the inverse trig function tan. So we'll take f of x equals tan, negative 1 of x, and take the tan of both sides so that this side just becomes x. So it's tan f of x is equal to x. And since we're doing the trig functions, we want to draw a triangle and see where that tan is going to be at on it. So tan is actually x over 1. And when I draw my triangle, it's tan is opposite over adjacent. So here's my x and here's my 1, and using the Pythagorean theorem, I find what the hypotenuse is, and it comes out to be the square root of x squared plus 1. So that's just there for right now. And then I come back over here, and I take the derivative of both sides, tan of f of x and x, and it becomes secant squared f of x times f prime of x is equal to 1. And then I'm trying to find what f prime of x is, so I divide both sides by secant squared x, f of x, and that is the same thing. 1 over secant squared x, f of x is the same thing as 1 over 1 over cosine squared f of x. And when you multiply by the whatever, it's cosine, you just get cosine squared f of x. And I know that cosine of f of x is 1 over square root of x squared plus 1. So since I know what that is, I can say that that is squared f of x. It's the same thing as that. I think I left out my f of x here. Oh, I don't need it. Okay. And this squared is, it just gets rid of that radical. Okay.
What questions for? You get all the steps? All those triangles can be really important really soon.
Can't help it.
So if you have questions about it, now's the time to ask. You good? Kevin, you good? You sure? My kids saw a lot of this last semester. They had to do this. So those of you who weren't in my last semester, some of the teachers just write those derivatives on the board. I don't know if you derived them or not. Some of them just say, here they are, memorized. Yeah. Any questions for me?
So secant squared equals 1 over cosine squared?
Correct, because secant of x is 1 over cosine of x. The definition of secant is 1 over cosine. That's the definition, AJ. All right, that AJ.
Yes.
Right. Secant is 1 over cosine, so secant squared has to be 1 over cosine all squared. 1 squared is 1. All right. Now, I don't want to pick on Andrea, especially after she did such a really nice job of doing that. But I also don't want Brandy to sick her on the test. What I told you I like equal signs, but I only like them where they need to be. Right? Right? This is equal to this, so 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 this is equal to this, is equal to this, is equal to this, equal to this, equal to this. 90% of them are right. Those, we don't need those over there, right? I know what you're thinking. You're thinking this is how I got from here to here, right? But tan inverse of x doesn't equal tan f of x. Right? So this doesn't equal this, doesn't equal this. Okay. All right, good? Okay. You're applying.
So we're integrating the parts. You just really pick your U's and your DV's. Plug it in. You got the U sub after that. So we get rid of this. So you use another variable. Just plug it back in. Integral 1 divided by f. It's log f. Just put them back together. Sub back and that's it.
Could you explain that again in more detail for me?
Me too.
What do you mean?
Whole thing over. Because I'm
Just
so
go through it
lost.
slower. You thought
Just
about it.
slower.
Let's go through it step by step and show them how you did everything. Just a little
you did it
slower.
right, just slower.
And louder, for those of us at the back.
Alright, so you're trying to integrate 10 raised to the negative 1 x dx. You're going to use integration by parts. The formula for that is uv minus integral duv. Alright, so I chose u as tan negative 1 times x. And the derivative of that is du equals 1 over x squared plus 1 dx. And dv, I chose dx. And the integral of that is just x. So I used the formula, plugged it in, and 10 negative 1 x times x minus the integral of x over x squared plus 1. The x comes from the v, as you can see. I just didn't really do all that work. Dx. And got the integral of this. So we use more variables, use sub. The reason I use 1/2 is to get rid of that 2 and the df. And then I integrated that, which is log f. Added both of these, that's why it's log f over 2. So it's x tan negative 1, x minus log f divided by 2 plus a constant. And then you have x tan negative 1 raised to the negative 1x minus log x squared plus 1 divided by 2 plus my constant. You just plug it back in there.
So you did it twice, starting at your first one, yeah, starting there, and then you broke apart. You substituted again. Using
So you had to use integration by parts and then use substitution. And do, right?
Yeah.
And you had to have memorized the problem that you just worked, that the derivative of tan inverse x is
Mhm.
1 over x squared plus 1, right? Now that's a really weird use substitution, isn't it? Because when you think of, a really weird integration by parts. Because when you think of integration by parts, you're usually looking for the product of two things, right? You're looking for an f prime times a g. And here, right, what's very odd about this one is that when you think of the integration by part formula, you think, I've got a product of two functions that I usually start with, right? You think of like integral of x e to the x dx, and you say, all right, I'll let my u be x, my du will be 1 dx, and my v dv will be e to the x, and my v, therefore, will be e to the x. And then I think of this as, the formula says uv minus the integral of, see, I did u dv. I use the FG notation. I'm going to confuse myself trying to use the uv notation. X, that's my u dv. So this must be v du. So uv, x e to the x, minus v du, e to the x. Right, you're used to thinking of, here's the two functions that I'm pulling out of here. I pulled that one out for my u, I pulled that one out for my dv. What's odd about it is that every once in a while, you'll let your u be this, and really what's your function for dv? It's really just 1, isn't it? The function that's, if you think of this in terms of like this notation, what you're thinking is tan inverse of x times 1. So your f is this, and your g prime is 1. So every once in a while when you do integration by parts, you don't see the product of two functions. And that's what can make that a challenge. But he did break it up right. There's his u, that's his derivative of u. There's his dv as dx, so that's like taking the antiderivative of just 1, so you get back x, right? The derivative of x is dx. That's a way to think of that. And then he breaks it up, and then this part, he had to do U sub to solve that part.
So he just instinctively knew that arctangent will become 1 over x squared plus 1 dx.
No. So he had his hand up for these problems too. He had to know that the derivative of f of x, tan inverse x, is 1 over x squared plus 1.
Okay.
Right? We had to do this problem first. We had to do this problem first in order to have a prayer of this one. Yeah, the notes are definitely in order except when I screw up. Which I think I did on inverse secant.
Okay.
Because I think the integral of inverse secant, to do it, I think you have to know a trig sub that I don't think you know yet. So every once in a while you don't know what you needed. But here, yeah, you had this one already. Then you had a chance at this. Yeah, and Chris, that brings up a real question about one of the things about the way I teach. So students sometimes ask, well, how would I have come up with this? Well, the answer is, in my calculus classes, there's so much material to cover that I let students look outside of class. Now, my preference is that you try every problem completely independently and see if you can get them. And the ones that just sink their teeth in and really try to get all of them by themselves end up going a lot farther mathematically, because just the process of trying to do all the problems by yourself before you go looking anywhere else or asking anybody for help will make you a better engineer or a better mathematician or a better computer scientist. Because learning to do things on your own is just an extremely valuable skill. And just like Scorpio back there, he wrote a whole bunch of steps of doing algebra and simplifying in the trig. Well, if I just told you to memorize the derivative of secant inverse x, he could have done that, but he wouldn't have been reinforced all those trig that he did as the process while he was discovering how to get where he got. Is there a little bit more efficient way? Yeah. Does it matter that we find the most efficient way? No. It just matters that we develop our skills at manipulating these guys. You got a question, Andrew?
I just, starting where you started the second integration by parts, I'm just confused. I don't
Not integration by parts on the second, just a U sub. He's just letting U equal x squared plus 1. He used f. He did an f sub.
Oh, okay.
Because he's already got a U up there.
So you didn't do it by parts twice?
No, the second one he just did right? You just did a U substitution called f is x squared plus 1. Then what's df? 2x dx.
Right.
So then what does this become? It becomes 1 over f. And then 1/2 df. That's 1/2 df.
How does it become 1 over f?
Because he made f be x squared plus 1. Oh, okay, here, I see your question.
Yeah, like what were the
Okay,
steps
let's just look at
in
that
this?
integral separately. We got x over x squared plus 1 dx. So let's let u be x squared plus 1. So du is 2x, right? dx. So this is the same as the integral of 1 over x squared plus 1 times x dx. Right? You multiply x times that, you'll put x over 1, multiply it, it'll end up being back there.
You just moved the x.
Oh, yeah.
So we just doing the algebra different.
Gotcha.
Now what have you got? You got 1 over u, what's x dx? It's 1/2 du, which he called 1/2 df. Taking through the half out front, yada, yada, yada.
Okay.
Yeah, so again, taking it back to the fact that I'm one of the only people in the math department that ever worked in industry. I'm your boss, I give you these problems. You got to come back and explain them to me. Well, one of two things happen. You might break the back of the problem yourself. You get it completely on your own without looking anything up. That's amazing. That's great. You come explain it to me. I know you understand. You know you understand it because you figured it out completely on your own. Option 2, you couldn't quite figure it out on your own. You went, looked up something, and got some ideas from it, and that helped you figure it out on your own. All that really matters when you come back to me is that you can explain it to me, right? Juan, did you look around anywhere on this, or did you do it on your own? Do it on your own, or you look on the website? Doesn't matter. You don't lose any points. Did you?
Looked around.
Looked around. Okay. So, but he still understands the steps. I mean, at least it was clear to me he understands the steps. We'll know whether he understands the steps when he takes the first test. But as long as you figure it out, what matters is you figured it out. If you figure it out first, completely independently on your own, like Jesse came by to see me in my office today, and he showed me a problem and did it completely. I've never even seen anybody do it that way. He used integration by parts on a trig problem, a few problems later in the notes. I've never seen anybody do it that way. Or if I have, I've long since forgotten it. But anyway, I know he did it himself because he couldn't. He did it a way I haven't seen. It's not. I guarantee you that's not the way it's done in any of the books. So, anyway, best to do it on your own. If you, but in my class, it doesn't hurt you any to look it up as long as you understand it. All right, I'm gonna skip over the inverse sign. Oh no, who's up? AJ, is that you? Go show me. Go show me. I'm sorry. I'm not gonna skip over that.